so what's the very first step that we need to do in any equilibrium constant question?
Find out our units.
Pardon? Figure out what our units are? Yeah, absolutely. Okay, so either we can write this out and write Kc equals etc. Well, moles to the dm minus 3, it's going to be to the power 2 because there's a balancing number of 2 in front of the HI. And then the units of the concentration of hydrogen are going to be moles to the dm minus 3, and the units of iodine are going to be moles to dm minus 3. Okay, what do you notice about my units? They're going to cancel out. So I've got mole to the dm squared here, and this is essentially mole to the dm minus 3 squared on the bottom as well. That's frozen. But what would have been a quicker way for me to do that? To see that there's no units? There is? So our balancing numbers are equal on both the left hand side and the right hand side. If that's the case, then your Kc is going to have no units. Alright, so next step is to rewrite our equation so that we can write everything underneath that. So we've got hydrogen reacting with iodine to give us hydrogen iodide. And if you space that out, so we have plenty of room to write things underneath. Oh yeah, it is. What's the first thing that we write on the left hand side down here? What do we need to work out first of all? Initial moles. What comes after initial moles? Reacting moles. And then good. I just abbreviate that to EQM moles. And then we won't, because it has no units, we can just use equilibrium moles rather than equilibrium concentration, so we don't need to work out our equilibrium concentration at the end. So that's all we need down the left hand side. So from my question then, I need to get my data for the initial moles. So what are my initial moles of hydrogen? Yeah, so it tells you of 1.9 moles of hydrogen. So I write that underneath my hydrogen. And how many of iodine do I have? Right, just the same, 1.9 of iodine. And then what's the initial moles of my hydrogen iodide going to be? 0. Yeah, 0. Initial moles of your products are always going to be 0. Alright, the other information I'm given in the question is that at equilibrium I have 3 moles of my hydrogen iodide. So I can write that in my equilibrium moles. So if you sort of go across, the equilibrium moles of hydrogen iodide is going to be 3.00 moles. Okay, what does that mean the reacting moles of hydrogen iodide is going to be? No, of hydrogen iodide. What did you say, Archie? Not minus 3. Products are always going to be... Yeah, they're always going to be positive. Okay, so if you remember, equilibrium moles is initial plus reacting. So if my initial moles of hydrogen iodide is 0, then what do I need to add to that to get to 3? 3. So that's going to be plus 3. Is that okay? Alright, but then we're on to the 1.5 here. Okay, no problem. So what are my reacting moles of iodine then? 1.5, because remember at this stage I need to use my balancing numbers to get my reacting moles. So my ratio here is 1 to 2. So I need to divide the number of moles of hydrogen iodide by 2, and so I have 1.5 moles of reacting iodine. But what's my sign? What does my sign need to be there? Minus. Okay, because my 1.5 moles of iodine is being used up. Okay, and then I do the same for hydrogen as well. Need to use my ratio. Again, my ratio is 1 to 2. And so again, I'm going to see that 1.5 moles of hydrogen is being used up, and so it needs to be a minus as well. Okay, equilibrium is initial plus reacting moles. So what are my equilibrium moles of hydrogen? Yeah, good. So 1.90. If you want to write that in, you can do that. Or you can just jump to the final answer. Like I'm being very generous. And then for iodine, what are my equilibrium moles? Yeah, exactly the same. And then we already have our equilibrium moles of hydrogen iodide, which is 3. Right, so now that we've got our equilibrium moles, and the fact that I have no units means that I don't need to work out my equilibrium concentration, I'm ready to put this into my expression for Kc, but I have to obviously write that expression first. So, looking at my equation, what's Kc going to be?
Hydrogen iodide squared over hydrogen squared plus hydrogen and
Great. So it's products over the reactants, and they're raised to the power of their balancing numbers. And then it's just a case of plugging my values in. So the equilibrium concentration of hydrogen iodide is 3.
Are these not mole values or not concentration?
Yes, sorry, put my moles in. But because there's no units, I don't need, I can just put the moles straight in. Okay, so it's going to be 3 squared over my value for hydrogen, which is 0.40, and my value of iodine, which is 0.40. Put that into your calculator, and you should get, great, 56.25. What do I need to write after that? No units. Okay, so these ones are a little bit more complicated, but hopefully not too much though. So what I want us to do now is, I've got a wee sheet somewhere that just helps us practice that idea of reacting moles, and I don't want to spend too long on it. I think there's about 6 of them. So you are given the initial moles and then one of the equilibrium moles, and what you have to do is work out what the reacting moles are and the other equilibrium moles. Okay, so the first example there is the formation of ammonia, so nitrogen reacting with hydrogen to give us ammonia. Okay, I'm just going to write initial reacting equilibrium. So we've been given that initially there's 1 mole of nitrogen, 1 mole of hydrogen, and 0 moles of ammonia. And the only other information we've been given is that at equilibrium I have 0.8 moles of nitrogen. Okay, what I need to do from that is first of all work out what my reacting moles are of nitrogen, and then use that to get my reacting moles of the other things in the equation. So how do I know what my reacting moles of nitrogen are going to be? Yeah, brilliant. So equilibrium moles are initial plus reacting moles. So if I rearrange that equation, then reacting moles is going to be the equilibrium minus the initial. So what is 0.8 minus 1? Minus 0.2. So is that okay? The other way you can think of that is what do I need to take away from 1 to get to 0.8? Is that alright? From that value of 0.2, then I use my balancing numbers to get my reacting moles of the other things in the equation. So what's the ratio of nitrogen to hydrogen? 1 to 3. So what are my reacting moles of hydrogen going to be? Yeah, and plus or minus? Minus, yeah, because it's a reactant, so it's being used up. What's the ratio of nitrogen to ammonia? 1 to 2. So what are my reacting moles of ammonia going to be? Plus 0.4. Okay, so from that then I can get my equilibrium moles. So for hydrogen, remember it's initial plus reacting. So for hydrogen it's going to be 1 minus 0.6, which is 0.4. And for ammonia it's 0 plus 0.4, which is 0.4. Okay, so give the other ones a go and see how you get on. Okay, so we're on page 20 now, and this is the last example of this type where we have to work out our initial and our reacting moles. Okay, so what's the first thing I need to do? Units. Okay, so the units of the concentration of SO2 are going to be moles per decimeter cubed. The units of my concentration of chlorine are going to be moles per decimeter cubed. And that's going to be over the concentration of SO2Cl2, which are going to have units of moles per dm cubed. So what do I see with this?
Your units are mole dm minus 3.
Yes, because this cancels out with that, and I'm left with moles to the dm minus 3, which is great. Now, what do you notice about what we've given and what we've been given with our initial amount of SO2Cl2? Yes, we're given a mass. So what do I need to do to that first of all? Yeah, I need to convert it into moles first of all. So, or you could even write initial moles of SO2Cl2. I can't just put the mass in. It's going to be mass over RFM. It is indeed. So it's going to be 6.75 over, should work out as 135. Oh, did you try it? No. You were just happy that you knew sulfur was 32 and then... Okay. Yeah. Anyway, that works out at 0.05 moles. So now I'm ready to put that into my equation as my initial moles. Okay, so I'll rewrite my equation with a wee bit of space in between it so that I can write everything underneath. So I've got SO2Cl2 dissociating to give me sulfur dioxide and chlorine. Okay, and when you're doing these, just go right ahead and write your initial reacting and equilibrium moles. So initial moles, reacting moles, equilibrium moles. Okay, this time I do have units. So what am I going to need to write underneath my equilibrium moles? Yeah, I need to this time work out my equilibrium concentration because I've been given a volume first of all, but my Kc has units, so that means that volume is going to affect the concentration. Okay, so my initial moles of SO2Cl2 I worked out as 0.05. Okay, what are my initial moles of SO2? 0, and of Cl2? So if you start with reactants, then the initial moles of your products are going to be 0. Okay, what does the question tell us? It tells us at equilibrium the vessel contained 0.0345 moles of Cl2. So underneath the equilibrium moles of chlorine, I can write 0.0345. What does that mean the reacting moles of chlorine are? Yep, and what sign? Yeah, plus. Sorry. Okay. It's going to be plus 0.0345. Okay, how do I work out my reacting moles of SO2? Yep, so my ratio is 1 to 1. So it's also going to be plus 0.0345. And then my reacting moles of SO2Cl2, again my ratio is 1 to 1. But what is my sign going to be this time? Minus, because I'm using up some of my reactants. Okay, then we need to work out the rest of our equilibrium moles. So that is again initial plus reacting. So what do we get when we take 0.345 away from 0.05? Yes, so we're adding these two, and we get 0.0155. What are my equilibrium moles of sulfur dioxide? 0.0345, because it's just 0 plus 0.0345. Hello? And then I need to work out my equilibrium concentration. What equation do I use for that? Kiva was in the middle of it. Go for it, Kiva. What equation do I use? Not moles times volume, but yeah, good. Moles over volume. Yeah, it's all Josh's fault. Okay, so what is my volume? Yep, my volume's 2. So look in the question, it tells you that it's a 2 decimeter cubed vessel. Okay, so for SO2Cl2 it's going to be 0.0155 over 2. For SO2 it's going to be 0.0345 over 2. And the same for chlorine. Divide those out, you should get 0.00775 for your SO2Cl2 and 0.01725 for the other two. Okay, happy enough at this stage? Yes, great. Okay, so I'm now ready to plug my values into my expression for Kc. But I need to write my expression first. So Kc is going to be equal to, it's the concentration of my products. They don't have any balancing numbers, so we don't need any powers, over the concentration of our reactants. Okay, then just plug in your values. So the concentration, equilibrium concentration of sulfur dioxide is 0.01725. Concentration of chlorine is 0.01725. And the equilibrium concentration of your SO2Cl2 is 0.00775. Work that all out and you should get 0.0384. And then I think to myself, what are my units? Well, I worked that out at the very, very start, and that is moles per decimeter cubed. Okay, so the next page, page 21, gives you an example of if you're given the percentage dissociation of a reactant. Now, this is not all that common, but you do need to be able to do it just in case it does come up. So basically, you're given the initial number of moles of your reactant, and it gives you a percentage of how much that dissociates. So that's the only thing you get. You get the initial moles and then the percentage dissociation. You don't get any other equilibrium moles or anything like that. But the only thing you need to think about is how much of your reactant is reacting. And so look at this question here. It asks you to find Kc for this reaction, and it tells you that HI, your reactant, hydrogen iodide, has undergone 22% dissociation. 22% dissociation. All that means is that 22% of your initial moles of hydrogen iodide has reacted. 22% of your initial moles of hydrogen iodide has reacted. So we can work out how much of it has reacted from the initial moles. So our reacting moles of hydrogen iodide are going to be 22% of the initial number of moles, which is 1. Okay, how do I work out what a percentage of a number is? Well, all I do is put the percentage over 100 and times it by the number. So my initial number of moles is 1. I'll circle it in pink here. Okay, What's 22 over 100 times by 1? Yeah, so in this case it's basically converting a percentage into a decimal. Is that okay? So that's what my reacting moles of HI are going to be. What is our sign for reactants, reacting moles? Yeah, negative. So that means that in this reaction, minus 0.22 moles of my hydrogen iodide is used up. Once you've got to that stage, it's just exactly the same as our normal ones. So first thing we do is what? It's units. But what I notice about my equation, yeah, so both sides of the equation have the same number of moles. So 2 on the right and 2 on the left. So what does that mean for my Kc? And it's units. There's no units. Great. So we can just write that. Kc equals no units. And if you want to make a note about there being the same number of molecules on the left as the right, that's why it has no units. If you want to do your multiplying out, that's absolutely fine. Okay, so then what we want to do is write our equation underneath. So it's just 2HI dissociating to give us hydrogen plus iodine. Okay, down the left I have my initial moles, my reacting moles, and my equilibrium moles. Why do I not need equilibrium concentration? Because you're not given the volume, and yeah, because there's no unit, so volume's not going to affect it. Okay, so what are my initial moles of hydrogen iodide? 1. So the initial moles, this value here, is 1.0. What's the initial moles of my products? 0. Always going to be 0. Okay, for my reacting moles then, I know that my reacting moles of hydrogen iodide is minus 0.22. Okay, and then how do I get the reacting moles of the product? Yeah, good. So I use my ratio, and that means I need to divide by 2 because the ratio is 2 to 1. So what are my reacting moles of hydrogen? Plus 0.11, and it's going to be then exactly the same for iodine because the ratio is 2 to 1 as well. Okay, so that stage is always getting it by the ratio. Equilibrium moles then is initial plus reacting. So what is that going to be for hydrogen iodide? 0.78 for hydrogen. And for iodine? Okay, now I've got my equilibrium moles, and because there's no units, I don't need concentration, so I can put these values straight into my expression for Kc. So looking at my equation, I can see that Kc, remember it's a concentration of your products over your reactants. So it's going to be concentration of hydrogen over concentration of iodine over your concentration of hydrogen iodide, but what do I need to do to that value? I need to square it because my balancing number is 2. Okay, at this stage I just plug in my values. So it's the concentration of hydrogen is 0.11, concentration of iodine is 0.11, concentration of hydrogen iodide is 0.78, and that's going to be squared. Multiply that all out, you should get, I don't have it written in, 0.0199. Is that right? And then afterwards I write no units, because there are no units. Okay, so this is for when you are given initial moles and you're given a value for Kc, but you're not given any equilibrium values whatsoever. no equilibrium values whatsoever. No dissociation value, no reacting moles, literally, thanks, literally nothing. It's not on my YouTube channel.
There's so much other worse stuff on it. I wouldn't worry about that.
Okay, so what you've got is a general equation here and how you would do a general format of it. Okay, so if you're not given any equilibrium moles, you have to take it as an unknown. So what we're going to do is we're going to represent the equilibrium moles of something as x, because it's unknown. Okay, now if it's on the right hand side and it's a product, is it going to be plus x or minus x? It's going to be plus x. And on the left hand side, yes, that was just basically meaning that it was going in the reverse direction. So this one is a wee bit simplified in that it doesn't have any balancing numbers. Okay, so this is just, say for example, you got a question, it was A plus B reacting to give C plus D, and your initial moles of A and B are 1. Okay, what we've done is we've taken, say for example for D, we've taken the reacting moles to be plus X. Okay, so we don't know what the equilibrium moles are, so we've taken it as an unknown. Okay, and what we've done then is used our ratio to get these values, and they're all just 1 to 1. And then equilibrium moles again is just initial plus reacting. So initial plus reacting here is 1 minus x. Initial plus reacting here is just x. Okay, so this is just a general one. There's a wee note there that we'll explain when we get there because it doesn't really make sense unless we do the example. But take the square roots. If any of you know about quadratic equations, you don't want to end up doing quadratic equations for this. That would just be crazy. And on that note, this question can only be, this type of question can only be for KC that doesn't have any units. Okay. Okay, so let's just embrace this and go for it. So looking at this example here, so I've got, again, we've seen this reaction before, hydrogen iodine reacting to give us hydrogen iodide. We've been given the Kc value and the initial moles of hydrogen and of iodine. So first thing we need to do is check our units, but what can we say about the number of moles on the right and the left? Equal, so it's going to be just no units. It's worth checking that, but this type of question won't have any units anyway. But just if you're not sure that it's this type of question, it's worth checking that. All right, what we notice with this equation, if I zoom in on this equation, what I've got here is 2 moles on the right hand side. Say for my reacting moles, I decided that this was plus x. What is my reacting moles of I2 going to be? Minus half an x. Do we like that? No, we don't. So do you know what we do instead? Yeah. So we take HI as 2x plus 2x, and that means that I2 will be minus x and H2 will be minus x. So really what you want to do is look at your equation, and for something with a balancing number of 1, make that x, like plus or minus x, depending whether it's a reactant or product, make that x. Rather than giving something with a balancing number of 3x, because then you're going to end up with a third x, and we just don't like that at all. So pick something that has a balancing number of 1 and make it x. But let's have a look at this. All right, so I've laid this out a wee bit for you. So what are my initial moles of hydrogen? No. 3. So it gives you that in the question. Initial moles of iodine? And then what will the initial moles of hydrogen iodide be? 0. Always 0 in our products. Okay. Reacting moles, so just explained that, we're going to take that as plus 2x for HI. What does that make it for I2? Minus x, okay, because the ratio is 1 to 2. And then we use our ratio again to get the number of reacting moles of hydrogen. What's that going to be? It's going to be minus x as well. Okay, good. So equilibrium moles is just initial plus reacting. Okay. So what's it going to be for hydrogen? 3 minus x for iodine. 3 minus x, and for hydrogen iodide, 2x. Okay, great. Now we don't know what x is yet, but we're going to put it into our value for Kc and try and find out what x is. So in this game, the aim is to find out what x is. It's a fun game. Just to warn you, this space is not very big at all. Like, look how squished it in mine is. So you're going to have to kind of squish this in. I apologise for that. Or do it on a bigger page. Yeah, something like that. Okay, so first thing is I need to write my expression for Kc. Kc is the concentration of your products over the concentration of your reactants, raised to their power. This is going to be the concentration of HI squared over the concentration of H2 times the concentration of I2. Okay, what do I do now?
Find your units.
We've already found them, but...
Oh, you have to do 2x squared as well.
Mm-hmm. So just sub in your values. Okay, so the concentration of HI is 2x. Concentration of hydrogen is 3 minus x. And the concentration of iodine is 3 minus x. And what does our question tell you that that's all equal to? 50. Okay, it gives you in the question that...
Where did you pull 50 from? Kc?
And says in the question Kc is equal to... So,
what are we trying to find out?
we're trying to find what x is so we can find out the equilibrium concentration of our reactants. Okay, so in this question you will always be given a value for Kc, otherwise you wouldn't be able to do anything with this equation whatsoever. Okay, so notice on the bottom I've got 3 minus x times 3 minus x. How can I simplify that?
3 minus x squared.
Great. So I'm going to write it and then I'll ask you if you're happy with it. So I'm going to keep 2x, I'm going to keep it squared at the minute.
Oh, I didn't sign up for this.
Is everybody okay with what I've just done?
I just don't like the fact that the x's and not actual numbers.
Yeah. Yeah.
I don't like that.
But we're trying to find what that x is. It's going to be a number eventually. But are you okay with how I've put 3 minus x to that? 3 minus x squared? Because something squared is just it times it by itself. Okay? How I can then simplify that again, if you don't mind me just moving on the way down. Okay, how I can simplify that down again is I can put 2x, because my top line and my bottom line are squared. Not quite yet. I can put that in a bracket and the whole thing is squared.
That is not similar to what you have in 2 seconds.
Yeah, but you'll see in a wee second why it is.
But what are we doing? Are we doing it not here under B?
No. I just have run out of room.
I got better as well.
I did warn you. Is everyone okay with that? If in a fraction you have the top line squared and the bottom line squared, you can put the whole fraction in brackets and make the whole thing squared. Because, like, say for example you had 2 squared on the top and 3 squared on the bottom.
Oh, you get like 9
Yeah, see, that just doesn't work out.
It's turned into quadratic.
No!
Because
that would be crazy.
That would be crazy.
Pardon?
No, how can you plus it like 2 times 4 and 2 times 8 and stuff like 3 2s? You mind?
Because that's...
But to give different
Because you're
options,
multiplying both by the same thing. With squared, you're multiplying them by different thing. I'm doing 2 times 2 and 3 times 3.
There you go.
There you go, indeed. Okay, at this stage, if I multiply this out and make x squared, I'm going to end up with a quadratic equation. Some of you might not even... I don't know, do you do that at GCSE?
Yeah.
Yeah, but you might not remember what it is. Anyway, you don't want to do it anyway. Yeah. So what I what I can do instead is, if I bring the squared to the other side, what am I doing on the other side? Yeah, great. So we talked a wee bit about this yesterday. So we're going to end up with 2x over 3x. I'm bringing that to the other side, and so it's the square root of 50. James, I told you about this yesterday. If something's squared on one side, you take the square root on the other side.
Yeah.
It's like the opposite. Okay? Fairly okay? Roughly okay?
Yeah.
Any? Somewhat okay? Alright, so how I'm now going to solve this is I need to have my x's added, so they need to be on the same side. But basically, what's my first step going to be to try and get the x's together?
Bring the 3 minus x here.
Bring that to the other side. So I'm going to bring this here. Okay. Yes, a wee bit of cross multiplication. If it's divided on the left hand side, what is it on the right hand side? Yes, great. So, or you can think of it as cross multiplying if you think of 50 being over 1. So I'm doing 2x times 1 is obviously 2x, and then 3x. 3 minus x times 50. Square root of 50, sorry. Okay, I'm just keeping that square root of 50 in because it'll just make it a wee bit more accurate for now. Okay, so, but now I'm going to multiply that out. Square root of 50 is 7.071, something like that. So if I multiply out this bracket, so I'm just multiplying everything inside the brackets by square root of 50, I get 21.213 minus 7.071x. Okay, I want my x's together, so what am I going to do now?
Bring it over.
Yeah, great, so I'm going to bring this over to the other side. It's minus on the right, so what's it going to be on the left? Plus, it's going to be 2x plus 7.071x equals 21.213. Simplifying that down, moving our x's together. That gives us 9.071x equals 21.213. How do I find out what x is? Divide. So x is 21.213 divided by 9.071, which is equal to 2.34. Yes?
Happy days. And there's no units, miss.
We haven't worked. This is not a value of KC. That was what my next question was going to be. Am I finished? No, I'm not finished, unfortunately.
You have to do like a 1 times x.
Right, so what I've done right now is I found out what x is, but the question asks me for to calculate the number of moles of each substance in the equilibrium mixture. So what I then need to go and do is sub this value of x into that. Okay, so if I move this all down here.
Hey miss, can I go so I can catch my bus?
Oh,
Hi miss.
see you later.
Tyler.
Okay, so what we need to do is substitute this into our values for our equilibrium moles, these ones here. So what I found out is that my concentration of hydrogen at equilibrium is 3 minus x. Are you happy enough with that? Are you happy with that? So the concentration of hydrogen at equilibrium is 3 minus x. And so what I'm doing now is I'm subbing my value of x in. So it's 3 minus 2.34, which is what we found x was. And so the concentration of hydrogen at equilibrium is 0.66.
Is this like a big
And units of, yeah, I'm sure it would be pretty crazy. So the concentration of hydrogen is 0.66 moles per decimeter cubed.
Right.
Okay, equilibrium concentration of iodine is also 3 minus x, which is 3 minus 2.34, which, funnily enough, turns out to be the same as hydrogen. Okay, and then we said the concentration of HI was 2x. So to get my equilibrium concentration of that, I do 2 times 2.34, which is 4.68 moles per decimeter cubed. So yes, this is an absolutely crazy question. Absolutely crazy. Just the very, very last bit, just very quickly. it asks you, I'll do this in blue here, it asks you to calculate the equilibrium concentration of HI in a volume of 10 decimeter cubed. All you do there is use your C equals N over V. Okay, so we've worked out here that the concentration of, the number, oh, I shouldn't have used those as, that's my fault, sorry, scored out those DM3s, because those are just equilibrium moles. Sorry, apologies.
Just those.
Yeah, it's just moles. Okay, so I found out that my number of moles of hydrogen iodide was 4.68 moles. Okay, it tells me that my volume is 10 decimeters cubed, so I just stick that over 10 decimeters cubed, and you should get your concentration of hydrogen iodide to be 0.468. Yes, it is. And now we're in moles per decimeter cubed.